This is lesson 3.3. Today we're going to talk about specifically what you have to write down for a simple random sample. We're going to do it two ways, using a piece of paper and also technology with random.org, which we did the other day in class. We're going to explain the concept of sampling variability and the effects of increasing our sample size. We're also going to talk about doing a simulation to test a claim about a population proportion. Okay, so our simple random sample the other day, if you remember with the Lincoln address, we had first started out with the address, right, the Gettysburg Address, and I asked you to just randomly pick five words in there and find how many letters are in them and find the mean. And this is our data. This is from first and second block data. Okay. So you can see it's pretty spread out. The mean was right around 6 or 7, a little bit over 6, or a median. So we overestimated. Okay, we overestimated because I think just by choosing these, a lot of you just picked, the words that stuck out to you, and there was some bias to that. Okay, then we did a simple random sample. The definition of a simple random sample: we're going to take a size n sample, so we chose 5 words, in such a way that every group of the individuals in the population has an equal chance of being selected. So what we did was we numbered, if you remember, we took each word 7 years ago, we numbered each of those words, and then we used random.org to randomly choose 5 numbers out of the 268 words that were there. Okay, so that was a simple random sample. Each word here had the exact same probability of being chosen, right? 1 out of 268 chance of being chosen. Okay, now that is an example of a simple random sample. So here's what we have to write when we look at this. We first have to give a label to all of them. Okay, so all the words we gave a label 1 through 268. We want to use a random number generator to select n different integers from 1 to n. So we chose 5 different words from 1 to 268. Then we have to state that we chose the words that were associated with the number we were given. Okay. Now one little side note here: if we chose a random number and and let's say the number was 237, we would have used the word n. Now, let's say we click that generate and another 237 pop up again. We would not want to repeat that word. We would want to choose another word, another number to associate with another word. So we don't want to repeat words that we've already used. Okay? So what I would write with that is I would say, okay, give each label. So we would say each word is given a number between 1 and 268. We're still talking about the Gettysburg Address, okay? So they have been labeled, okay? Then we will use a random number generator. We used random.org, okay, to select 5 unique numbers. Okay, so in random.org, I used it and chose 5 numbers from that randomly, and unique means they have to be 5 different numbers. Okay, then the select part, we're going to choose the word associated or assigned to those 5 numbers to survey. Okay, so that's kind of the process when you're talking. If I ask you to describe a way to sample using a simple random sample, you want to use this idea. Each word is given a number. We will use a random number generator to select 5 unique numbers, or however many you want to find. And then you're going to choose the people or word associated with those or assigned those 5 numbers. Okay, so that's kind of what you need to have in there. Now, another way to do this is the paper slip method. Okay, so I could take the Gettysburg Address here. What do I do with it? Okay, I could take the Gettysburg Address. I could cut out, I could put, okay, so to make it them all have the same chance, I could put each word on identical pieces of paper. Okay, so I can't just cut this out and then cut this one out, because this one's going to be a little longer than this one. Okay, we need each piece of paper to be identical. Okay, same shape, same size. And that way, when it's put into a hat and picked out, each of them have the same chance of being selected. Okay, so put each word on identical pieces of paper. Okay, okay, so that's the labeling part. Okay, the randomize, we're going to put the paper into a hat or box or whatever and mix them. Mix the paper. Okay, when I mix that paper together, that gives me the randomizing part. Okay, so we did the labeling, we did the randomizing. Okay, then we're going to select. We're going to select, in this case, 5 pieces of paper. And use the words on each piece. And those are our sample. Okay, so 2 different ways that you can get a simple random sample. Each of them we have to label how we're doing it. Okay, we'll have to randomize it, and then we'll have to do the selecting. Okay, so we label it, randomize it, and select our sample. Okay, so that's the whole idea of a simple random sample. Okay, I'll show you this example here. Okay, when landfills run out of room, they are sometimes converted into parks. Does the presence of a landfill underneath affect the trees that grow in the park? So that's our statistical question. So they went to one park, which had 283 trees, and they wanted to closely inspect a sample of 20 trees. Okay, population, sample of 20 trees. How would they do a simple random sample using slips of paper to select those 20 trees? Okay, one way, give each tree a distinct label from 1 to 283. So we're labeling each tree, tree number 1, tree number 2, tree number 3. We're going to number that many identical sizes slips of paper. We're going to put the paper into a hat and mix it. That's the randomizing. Then we're going to pull out or select 20 slips of paper and inspect those 20 trees labeled. Okay, so that's the idea with the slips of paper. Using technology, we're going to give each tree a distinct label from 1 to 283, labeled tree 1, tree 2, tree 3. We're going to use a random number generator like random.org to select 20 unique numbers, ignoring repeats, that means and then we're going to inspect the 20 trees that are labeled from that. Okay, so that's the idea of a random number generator. Okay, so we had also talked about looking at this data. This was when you just randomly chose numbers. This is when you had a sample of size 5 that we chose from the Gettysburg Address. Now, the true mean, I'll just tell you, the true mean was 4.26. So you can see here that we overestimated almost all of them, okay? Because your eyes were drawn to the bigger numbers and you chose the bigger numbers to choose, okay? That was biased. Okay, now, when we did a simple random sample, when you chose 5 words from our list using random.org, we got this. 4.26 looks like a pretty good center of our data, right? Okay. And we have a certain spread to it. Now, what if instead of choosing just 5 words, I choose 10 words to sample? How do you think that's going to change what this looks like? Do you think our center is still going to be at 4.26? Do you think is going to happen to our spread? Okay, if I choose more numbers in my sample, so when I'm looking at this list, I'm choosing 10 random numbers instead of just 5. So instead of 5 words, I'm choosing 10 words. Do you think I'm going to get more accurate? Is it going to be a better sample? So I think my center would still be at the same place, but my distribution, if I take 10, it's going to take this variability and it's going to reduce it. So I'm going to have more numbers that are closer around the true mean. Okay? So if I have more in my sample, there's less variability. It's less spread out. Okay? That's the second thing we want to talk about. So number 1 was how we described this simple random sample. Number 2, what does sample size do? Sample size will reduce our variability. The center will still be the same center, but it'll be less spread out because taking more in our sample would be more accurate data. Here's another little example. This is with word zones again. They did other papers instead of the Gettysburg Address, but with word length of 5, you can see it's very spread out. But if they take 20, a lot less spread out. Still the same center, right? Still around the same center, but less spread to it. Okay, so let's look at this problem. The median household income in a random sample of 371 Virginia households is $61,784. Do you think that the median income of all households is equal to this? So this is our sample that we collected. Do you think the actual true median is exactly this number? No. Okay. When we collect a sample, it's going to vary a little bit, right? Our sample is probably not exactly on. Okay. Part B, if we, instead of taking 371 households, what if we took 1,000 households? What will that do on the median income? Okay. So the more that we take, the more accurate it's going to be. So it's going to be closer. Our center is probably going to be centered better, and it's not going to be as spread out. So the more that we take, to be closer to the true median and less spread out. Okay, the next example here is sampling, inference for sampling. So can we really say, we take a sample, can we say that's true about the whole population? Okay. Now this is a little bit harder to grasp, so you might need to watch this a couple times and ask me questions about it. So here's a question. Can you taste the difference between a store brand and name brand cookie? So if we were in class, I'd probably bring you a cookie, and I'd give you, and you could choose which cookie you wanted and tell me if it's a store brand or what. Okay. We're going to take 30 selected high school students were asked to taste 2 unlabeled cookies and identify which cookie they preferred. One of these cookies was name brand, which was Chips Ahoy, and the other was some store brand, like Kroger brand or Chipmates or whatever, okay, some cheaper brand. The order in which the 2 cookies were presented was determined at random with a coin flip. So if I flip a coin, heads, you got this one, and tails, you got this one. So about half the time people got that, about half the time people got that. Of these 30 students, 19 of them preferred the store brand cookie. Okay? Now, do you think they could really tell which was a store brand cookie and which not, if 19 out of the 30 chose the store brand cookie? Okay? So we're going to do a little simulation. Okay? So there's 2 different things. You could either get the store brand or the off brand. Okay? The name brand or the store brand, right? Okay. So can we tell a difference? Name brand's usually more expensive than store brand, right? Is there really a difference between those cookies? Okay, now, if I just give you 2 cookies at random, there would be a 50-50 chance. If you really couldn't tell, there would be a 50-50 chance that you would be able to choose which one's the name brand, right? So out of 30 cookies, we would think if you really can't tell the difference, about 15 out of the 30 times you would be able to choose the name brand if you really couldn't tell, half the time, right? Now, sometimes, that's going to vary. If I take this group of 30 people, usually about 15% of the time, they would be able to tell which one it is, right? 15 out of 30 times. But if I take another group of 30 people, they might have 16 people that can guess, okay? And sometimes if I take another 30 people, I might have 14 people that guess the name brand, okay? This is a number that guess the name brand cookie, okay? So if we would do this over and over and over again, we would get some variability. So this is an example. This graph right here is an example. If we take a simple random sample of 30 people, how many, like, so for example, this one right here would be that 21 out of the 30 people chose the name brand. We said on average, we would probably have about 15 out of the 30 people, right? That's why that one's a little bit taller. Sometimes 16, 14, right? This would say that only 9 of the 30 people chose the name brand as their favorite, okay? So there's 100 little dots here. So we did this, it'd be like me giving the class of 30, we would do this like 100 times, okay? You might get sick of cookies after that, but anyway, okay? So our results were that we got 19 people in this one class, 19 people got the store brand. Now, is that a high enough percentage to say that, okay, 19 out of 30 gives you 63% of the time? If they were able to pick the name brand cookie 63% of the time, does that really mean that this name brand cookie is better than the store brand cookie? Okay, that's the question. Or could it just happen by chance, right? So this is, if there's really no difference, this is the distribution that we might have. So if we had 19 or more, okay, that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We had 10 out of the 100 people say that that would just guess that much. That's it. So 10 of the 100 simulations resulted in at least 19 successes. Because the result of 19 or more successes isn't that unlikely, right? 10 out of 100 is not that unlikely. Mr. Powell's class decided there wasn't convincing evidence that students at the high school could prefer the name brand cookie. It might have just happened by accident that they chose that name brand cookie. In other words, it is plausible that the two brands of cookies are equally preferred, and the result of 19 out of 30 could have happened just by pure chance, just because there is some variability when you choose. This idea we're going to work with a lot later on, so kind of develop an idea of what this means. Okay? Here's another example. Do students have a preference for the last thing they taste? So research at the University of Michigan designed a study to find out. The researchers gave 22 students 5 different Hershey's Kisses. There's milk chocolate, dark chocolate, cream, caramel, and almond. So lots of different kinds. In a random order, and asked the students to rate each one. So sometimes some people got them in this order. Sometimes they got the cream last. Sometimes they got the caramel last. Sometimes they got the dark chocolate last when they tasted them all. Students were not told how many kisses they would taste. However, when the 5th and final kiss was presented, their participants were informed that it would be their last one. Of the 22 students, 14, which is 64%, 14 out of the 22 students, gave the final kiss the highest rating. Okay, now, if there were 5 of them, I would expect, if there's no difference between them, 1 out of 5 would be 20%. Okay, there would be a 20% chance. But here we had 64% of them choose the last Hershey Kiss they got. So if we really couldn't tell a difference, 20% of the people would choose each of the 5 kisses. Okay, so to determine if this was convincing evidence that more than 20% of the people really did taste it, They did a simulation. So they did this study basically 100 times. Okay. So 20% chance. Okay, so part A. Explain how the graph illustrates the concept of sampling variability. So if researchers repeatedly take samples of size 22 from a population, okay, so they did this experiment many, many, many times, okay, this shows you the number in the sample who prefer the last one, okay. It tells us that it ranges from about 1 to 10. Usually we prefer 1 to 10 people preferring that last one. If there's no difference between them, there really is no difference. They would choose in the equally likely. Between 1 and 10 people would choose the last one. Okay, but based on this result, we had 14 people choose the last one. Do we have anything out here that any people that chose, where there would be 14 of them? Okay, there is convincing evidence. There are 14 people that preferred the Hershey Kiss they taste. It's much greater than what we would expect to happen. We would expect maybe 3, 4, 5 people to choose. But we had 14 people choose. Therefore, we can say we have convincing evidence that people like the last one more than all the others. It makes a difference in the order. Now, that's all kind of complicated, okay? But that we'll work on that a little bit more. Last example. Question is, what proportion of students at your school use Twitter? To find out, you decide to take a simple random sample of students at your school. So describe how you could take a simple random sample of students, of 50 students, okay? So you could use the paper slip method or the random.org method, okay? Paper slip method. You could put everybody's name on a piece of paper, mix the papers, choose the papers, okay? Choose the 50 students. Random.org. Number all the students, 1 to whatever. Use a random number generator to select 50 numbers. Choose those 50 students. Okay, so you could write one of those two things. Will your sample result in exactly the same as the true population proportion? So if the true population proportion is, I don't know, 70% of the people use Twitter, will your sample give you exactly 70%? No. You're going to be somewhere around 70%. Maybe you get 70%, but you'll get somewhere around there. Now, which is going to be more likely to get this true, say the true proportion is 70%? If you take 50 students or if you take 100 students, okay? 50 students, if this is my true proportion, 50 students might have an average of there, right? But if I have 100 students, I'm going to be more closely bunched right around that true number we're trying to find. Okay? Those are the notes for today.